Hi, and welcome back, Allen High School kiddos. We're talking about enthalpy and free energy right now. Or it's not free energy, just the enthalpy and MCAT right now. And I want to look at calorimetry in a little bit more detail. We're just going to look at variations on the theme of MCAT. Now, when we do calorimetry in the lab, we're going to do an experiment with this. We're actually going to use two styrofoam cups. They are surprisingly good little calorimeters with a cover. Now, the difficulty here is being able to distinguish between our system that we're talking about and its surroundings. So often the system there's a little bit of a gray area. It's not physically separated from the surroundings very well. That's what happens when we have solution reactions. The system is the place at which the bonds are being broken and new bonds are being formed. And the surroundings can be the bulk solution and the calorimeter itself. Each and every component of the calorimeter has potential to absorb heat. So we would say that Q for our process, whatever it is, it's a dissolving or reacting or neutralization, not a combustion in styrofoam. Okay, Q for our process equal and opposite in sign, all right, as Q for our surroundings. All right, so if our process releases heat, then the surroundings should gain heat. If on the other hand, our process is sucking in heat, then our surroundings should lose heat. So in an ideal situation, they're equal in magnitude but opposite in sign. Now, when we have a calorimeter like this, we would say that Q for our process, let's just call it a process because it might not be a reaction, is possibly equal to Q for, it's either going to be a bulk solution or water. There will be a situation where we'll talk about water there, plus Q from the calorimeter. Okay. Now, it's not uncommon to neglect that contribution from the calorimeter. We're going to start with a couple of problems where we neglect it, and then you'll see what we do to add it back in. So let's take a look at this example. Sorry, I had that on another page for you so we'd have more room, but Mimeo kind of messed up my formatting there. So let's take a look at this question right here. We have got 1.095 grams of NaOH dissolved in 150 grams of water in a coffee cup calorimeter, and we have a T1 and a T2. Now, it gives us a hint here. Remember, we can communicate verbally. If heat is liberated, we know we're looking for an exothermic process. So Q of our dissolving is going to be equal and opposite in magnitude Q of our bulk water solution plus Q from the calorimeter. Now, this problem specifically says assume that the calorimeter didn't absorb any of the heat and that it's just the bulk solution. Sometimes it doesn't say that, but you have no choice but to make that assumption because you're not given any information about the calorimeter. So Q for my dissolving process is going to be equal in magnitude, opposite in sign to what happens to the water. So I'm talking about the water, so I use 150 grams of water. It says I can use the heat capacity of water. In other words, the sodium hydroxide that's dissolving isn't altering the heat capacity of the water too much, times my delta T, 25.32 minus 23.50. We're back to final minus initial all the time. Okay, the only time we don't use that is bond energies. It's a little sloppy. I'm sorry about that. There we go. 3. All right. So if you do that calculation, what you're going to get is minus 1151. This was in joules, so this is going to be joules. Now, that's joules for 1.095 grams of NaOH. It didn't ask me per mole or anything. We're going to do that on the next problem. So let's take a look at it. So this time we have magnesium chips and we're reacting them with HCl. Now, it's not uncommon to see situations where they say, assume that that hydrochloric acid solution has the same heat capacity as the water, and assume that the densities are the same. And if you're not told otherwise, that means that the density is 1 gram per milliliter. Now, some of you are going to want to take this 100 mLs and try to find the moles of HCl, but the problem doesn't ask us anything about per mole of HCl. The problem asks us to determine this per mole of magnesium. So we don't have to worry about the moles of HCl at all. So Q of our reaction is equal to minus Q of our bulk solution plus Q of the calorimeter. Well, it doesn't say anything about a calorimeter, but it also gives us no information on a calorimeter. So we have no choice but to assume that we're going to neglect that. So then it's minus my mass of my solution. I had 100 mLs. It told me to assume the density was the same as water. So I'm going to call that 100 grams times 4.184 joules per gram degrees Celsius, and that's for the water. We're assuming that's the same for the bulk solution. That's my final. It's always final minus initial with the exception of bond energies. By the way, have you started reviewing for that AP test? It would be a really good idea to make sure you're doing that by now. 9.46 times 10 to the third joules. Now, that was for not a mole of magnesium. That indeed was for 0.500 grams. So that was joules per half a gram. The question asked us joules per mole. So I want to eliminate grams and go to moles. There's a couple of ways you could do this. Some people would convert that to moles and then do their dividing. It doesn't matter. It all works out in the end. This is 24.31 as long as your units cancel in the end per 1 mole. And when all is said and done with that algebra, I got something a little different than that when I did the algebra again. I got 4.60 times 10 to the 5th joules per mole of magnesium. Didn't ask us per mole of HCl. In this case, the HCl was very likely in excess, and my magnesium was my limiting. So you always want to have it per mole of your limiting reagent. Okay, I want to do one more, and this time we're going to include a calorimeter constant. We're going to react sodium bromide with silver nitrate. And I hope you know by now, reactions are very important. We're going to have sodium nitrate, really sodium ions and nitrate ions swimming around in the bulk solution. And silver bromide is going to precipitate. So Q for this double replacement reaction is going to be equal and opposite in sign to Q of my bulk solution plus Q of my calorimeter. Now, if you'll notice, with the calorimeter, there's no mass term in here. That calorimeter constant, that's what it's often called, calorimeter constant, is specific for this calorimeter of this particular mass and is not transferable to a family of calorimeters. It's for the particular one we're doing. So we have a 50-gram sample of a 0.2 molar sodium bromide is added to a 50-gram sample of 0.2 molar silver nitrate, and that gives us a total bulk solution mass of 100 grams. Now this time it gave us a heat capacity for the solution. It's slightly different than 4.184. It's 4.20. And my temperature change ended at 25.04 and it started at 23.65. Now, the calorimeter, there's no mass, it's just a calorimeter constant, has the same temperature change, 25.04 minus 23.65. It is assumed that the bulk solution and the calorimeter are in thermal equilibrium with one another. And Q, in this case, it's constant pressure, so we could call that enthalpy, is minus 849 joules. It's logical since temperature increased. If temperature of the surroundings increase, it's exothermic. Now, that's just per joules, or per the sample. It doesn't ask us to calculate per moles of sodium bromide, but we could because, we could change this to volume. We'd have to assume a density of 1, and then we could take volume times molarity and get moles of sodium bromide, or we could do it for the silver nitrate. They are both limiting in this case, and we could get it per mole, but it didn't ask me, so I'm not going there. All we would have to do is take that 50 grams, let's go there, okay. Liters times 0.200 moles per liter. Okay, that would give us moles, and if we divided those joules by those moles, then we would get the molar value on a per mole basis rather than just for the reaction as it was. Okay, the next one we're going to look at bomb calorimeters. I wish I could buy one of these. They're rather expensive, and I need oxygen, pure oxygen for them, which we don't like pure oxygen tanks hanging around the room where we have Bunsen burners and flammable things. So we just get to talk about it. And so until we have that opportunity to talk about it, this is your best chem teacher signing off.